Have you ever wondered how a rainbow forms? Or even just looked at your own reflection in a mirror and thought about what's actually happening? Well, our world is absolutely governed by the fascinating behavior of light. And while it can seem super complex, it really just boils down to a few fundamental rules. So in this explainer, we're going to pull back the curtain and demystify the world you see every single day. All right, let's start with something you've probably done 1,000 times. You pick up a shiny spoon, you look into the part that holds the soup, and boom, your face is upside down. Then you flip it over to the curved back, and suddenly you're right side up, but all stretched and distorted. So what on earth is going on there? This simple little experiment is actually the perfect gateway to understanding how curved surfaces can twist and turn light. To get to the bottom of the spoon mystery, we first need to know that light is actually incredibly predictable. It follows two main sets of rules, no exceptions. You've got the laws of reflection, which is what happens when light bounces off a surface, and then you have the laws of refraction, which covers what happens when light passes through something and bends. So let's break down the core difference right here. For reflection, it's honestly pretty simple. The angle that light hits a surface is exactly the same as the angle it bounces off. It's like a perfect bank shot in pool. Now, for refraction, light actually bends when it goes from one thing to another, say from air into water. The light ray still stays on the same flat plane, but its angle changes. And it changes according to a very specific rule called Snell's law. And that brings us to this really crucial idea, the refractive index. The easiest way to think about it is as a bending power score for any given material. The higher the refractive index, the more that material slows light down and the more sharply it bends it. So something like a diamond has a really high score. And this formula you see here, N equals sine I over sine R, that's Snell's law. It's the mathematical heart of how all refraction works. Okay, so we've got the basic rules down. Now let's build ourselves a kind of masterclass, a cheat sheet really. This next part is all about being able to predict exactly what kind of image you're going to get from a mirror or a lens just by knowing where you put the object. Let's go back to the inside of that spoon. That's a concave mirror. Now look at this table. You'll see a really clear pattern here. A real image just means it can be projected onto a screen, and inverted means, well, upside down. So notice that when an object is really far away, the image it creates is tiny, real, and inverted. But watch what happens as you bring that object closer and closer to the mirror. The image gets bigger and moves farther away. The big takeaway is that everything changes in a predictable way. Now let's switch from mirrors to a convex lens. Think of a classic magnifying glass. Take a look at this table. Does that look a little familiar? It should. It's almost identical to the concave mirror we just looked at. And that's because they're both converging, which is a fancy way of saying they bring light rays together. A concave mirror does it by bouncing light inward, while a convex lens does it by bending light inward. It's the same result, just a different method. Pretty cool, right? And now, we get to the part that trips up almost everyone, the math. Seriously, the formulas themselves are actually pretty easy, but if you get the positive and negative signs wrong, the whole thing falls apart. So let's really nail down the new Cartesian sign convention. This is the absolute key to getting every single problem right. Just think of this like a simple graph from math class. The very center of the mirror or lens, that's your origin, your 0 point. We always assume that light travels from the left to the right. That means any distance you measure to the right of the center is positive, any distance to the left is negative. And for height, anything above that center line is positive, anything below is negative. That's it. That's the whole system. You know, I'm going to let this sit here for just a second because it is that important. I'm not kidding. Getting these signs right is literally the difference between the right answer and the wrong answer on pretty much any calculation you're going to do. Every single formula we're about to look at depends on you knowing these simple rules. All right, now that we're masters of the sign convention, let's look at the tools we're going to use it with. When you boil it all down, there are really only 3 main equations you need for almost any mirror and lens problem you'll ever face. First up, we've got the mirror formula. It's this really elegant relationship between the object's distance, which we call u, the image's distance, v, and the mirror's focal length, f. Just 1 over v plus 1 over u equals 1 over f. It's simple, it's powerful, and it works for all spherical mirrors. Next up is the lens formula. Now look really close here. It's almost the exact same thing as the mirror formula, but there's one tiny critical change. See it? That minus sign. 1 over v times minus 1 over u equals 1 over f. That little minus sign is the only thing separating the math of reflection from the math of refraction. And last but not least, magnification. This one just tells us how much bigger or smaller the image is compared to the actual object. The formula couldn't be simpler. It's just the image height divided by the object height. If you get a number bigger than 1, the image is magnified. If it's less than 1, it's smaller. It's really that straightforward. Okay, so we've covered the laws, we've looked at the tables, we've mastered the signs, and we have the formulas. But why does any of this actually matter? Well, let's connect all of it to something you see every single day. The mirror on the side of a car. You know that little warning text on your passenger side mirror, right? Objects in mirror are closer than they appear. That's a massive clue. The type of mirror used in a car is not a random choice. It is a direct application of the physics we've just been talking about. So why on earth do we use a convex mirror? And here's the answer. First, a convex mirror will always give you an upright image. I mean, you definitely wouldn't want to see the car behind you upside down, right? Second, the image is always diminished or smaller, and that is the real key. By making everything appear smaller, the mirror can actually show you a much wider field of view. It helps you see more of the road and cover your blind spots. It's a safety feature that's born directly from the laws of physics. And in the end, it all comes back to this one simple, incredibly powerful idea from the source material. It doesn't matter if it's a spoon, a car mirror, a telescope, or your own eyeball. The rules are always the same. Reflecting surfaces follow the laws of reflection. Refracting surfaces follow the laws of refraction. Period. Now, for everything we've talked about today, we've treated light like a simple ray traveling in a nice straight line. And that model works perfectly for mirrors and lenses. But the rabbit hole goes so much deeper. What happens when light stops acting like a line and starts behaving like a wave? Or, even weirder, like a particle? Well, that's a question for another time.